thanks a lot for having me. It's my first time in India, and it's kind of crazy, but I'm loving it so far. Loving the food, obviously. Today's actually a historic day for the Emirates, and that's not well. There's a first for the Emirates. That's not just that the first theoretical physicist is giving the first talk in India. It's because it's actually the first Emirati astronaut is being launched into space today.
Okay. In what vehicle?
Through the Russians.
Okay.
Yeah. I guess it's also a historic day for the world because the impeachment proceedings of Donald Trump are starting. So I don't know which one makes me happier. But anyways, it's a nice day nevertheless. Okay, so let's get started with these lectures. So, so the focus is going to be on a recent set of, I think, significant updates on the information paradox, which appeared in a few papers in the last few months, made possible due to two factors. The first being insights gathered from holography, namely the computation of holographic entropy. And the second comes from identifying a class of solvable models, that being, for example, SYK and JT gravity, which might seem deficient in some ways, but I will argue that they retain surprising features that are expected to hold in more realistic, higher dimensional gravitational systems. And we can fight about that later. The goal of this first lecture is to introduce the problem, which I will do entirely in the language of the model that I'm going to consider, which is going to be JT gravity. And the goal is to confuse you as much as possible. Okay, so let me begin by reviewing the model. So I'm going to consider JT gravity coupled with conformal matter. The conformal matter is coupled only to the gravitational sector, not to the dilaton. The action of the JT sector is given by this, which I'm sure everyone here is familiar with. Phi is the dilaton. For the moment, let's focus on the JT part of the action, and let's discuss how that part is solved. The idea is that we have to look for solutions with the following ADS boundary conditions on the metric, and the following boundary condition on the dilaton. These boundary conditions define the theory. This coordinate u should be thought of as the boundary proper time. And epsilon is like a holographic direction. It's like the z direction away from the boundary. The first step in solving this model is to notice that one can perform the path integral over phi, say
So
which.
what does twiddle mean? Is it phi twiddle? Is it approximately?
I don't know what the prefactors are and so on.
Did you mean for the upstairs?
Yeah, for the upstairs, yeah.
Oh, here?
Yes.
Oh, it's equal to as epsilon goes to 0. Yeah, asymptotically. Thank you.
What is u?
U is a boundary proper time. Okay. Okay, so the first step in solving this model is we notice that we can do the path integral over phi. We can choose a complex contour or a contour along the imaginary line.
Sorry, but I mean, if I do a coordinate change in u, if it's proper time, its metric would be 1, right? I'm not understanding how that coordinate is defined.
Oh, I just mean this is the proper time on the boundary metric. So the way you get the boundary metric is that you strip off this factor.
So boundary metric by definition is epsilon squared times
Exactly.
metric.
In the limit as you go to infinity.
So this is then a choice of coordinates. GUU is not an invariant.
Yeah, sure. No, but I mean, this is the usual way we do ADS-CFT, right? We don't do large. So coordinate transformations that change U are large coordinate transformations in the context of ADS. So those are not diffeomorphisms.
Okay. So there's a distinguished time on the coordinate.
Exactly.
Okay.
It's what you would have done, but you strip off the epsilon.
Okay. Now, the next statement to notice, again, is that you can do an integral over phi, which completely localizes the metric to be hyperbolic space, and which means that we can work in a, we can choose to work, let's say, in Poincare gauge in the bulk, where we can write the metric as something like this. Sometimes well, these null coordinates are often convenient. And the idea now is that given working in this gauge and using these boundary conditions, we arrive at the following equation relating these Poincare coordinates to epsilon, at least asymptotically. You find that the location of, well, let me see. Well, this thing solves, so you can solve this to get something like this. You find that this, maybe I shouldn't choose the picture first. This process essentially tells you where the location is of the boundary embedded in the Poincare patch or in the Poincare coordinate system. And solving that equation pins down for you, as I said, the location of this curve, given basically the statement is that given what is called the reparameterization between Poincare time and boundary proper time, one can plug that into this equation and find the z location of this what is often called the boundary particle. That's where you should think of the boundary theory dual to the ADS2 as living. Okay. These details are actually not going to be that important for the rest of the talk, but I thought I'd explain them for completeness.
I'm sorry, I know for most of your work just being the semi-classical approximation, but just since you bring up this point, if you really were to try and quantize JT like some others have done, then you have to worry a little bit about the exact contour of integration for phi and its range of integration as well.
Mm-hmm.
For example, to the extent that one might think of JT model as a dimensionally reduced version of a higher D carry, then phi doesn't go from, say, minus infinity to infinity, etc.
Mm-hmm.
So there can be interesting variants of the model.
Sure. Yes.
From
Yes.
that perspective, but of course I know that.
Yeah. So that's a good point to bring up. Okay. So this T of U, as I said, is called the reparameterization mode. It is the only dynamical degree of freedom in JT gravity, and its action comes entirely from the boundary term, from this extrinsic curvature term, where if we evaluate it on that metric with this solution here, one ends up with this action, which is famously now called as the Schwarzian action for obvious reasons. This is the Schwarzian, which governs the dynamics of this boundary particle. Okay, one can also get, so this analysis is near the boundary. One can get bulk Einstein's equations just by doing the usual thing. You vary with respect to the metric, and you get an equation that looks like this. Some differential equation, some differential operator acting on phi is sourced by the expectation value of the CFT stress tensor. Okay? Here I'm imagining working in the semi-classical limit, which just means that the geometry is sourced by the expectation value of the stress tensor, right? Because the CFT is a quantum thing. An interesting class of solutions are the vacuum solutions, where we plug in for this as just 0, and that solves for something that looks like that. So this is using the Poincare coordinates. And the reparameterization between Poincare time and boundary time is just a tan hyperbolic. It's very simple. So what it looks like is something like this. It starts and ends and at finite points in t. So here, this point here is when u goes to infinity. T goes to, I guess, 1 over pi t. And at this point, u goes to minus infinity, and t goes to minus 1 over pi t. Okay. So there's a convenient set of coordinate system to work with in this case, where so this solution right now looks complicated, but it's actually a very simple solution. It's actually a static solution, provided you work with the right coordinates.
So do I remember right? There was in general a three parameter set of solutions for phi,
That's right.
and you've chosen one of them.
Mm-hmm.
Why did you pick that one out?
It's just convenience.
Okay.
I can. They're all related by SL2 transformations. Yes.
The expectation value is taken in some vacuum state. This is the vacuum state you have. The one that you have chosen is the one that is vacuum with respect to, let's say, the Poincare time.
Yes. That's right.
We could have chosen different states.
So yes. So now we're saying that yes, this is the Poincare vacuum. Okay. Yeah. So now there's a nice coordinate system. Is y plus minus, which where the time in this null coordinate is the same as the boundary proper time, or the physical time, often it's called, and some distance sigma. The relation between these new null coordinates and these x plus minus null coordinates is the same function, just tan hyperbolic, in which the dilaton attains a static form. It depends only on sigma.
Sorry, that t was the solution of that equation? No. Oh, sorry.
Yes, this t is a solution of well, you can derive it in many ways. One way you can derive it is by obtaining the equation of motion in terms of the Schwarzian theory. So the Schwarzian theory also is sourced by the stress tensor. So the equation is actually du Schwarzian is equal to something like t plus plus minus t minus minus. Looks something like that's what the equation is. But this is all 0. So the equation we have is that the Schwarzian is equal to some constant, E naught, let's call it. I said E naught because actually the Schwarzian ends up being the energy. So solving this equation gives you this. And solving these equations give you that. But these are actually the same equations. I should emphasize that.
Which are the same equations?
Solving this equation or solving this equation. Given the boundary, they're related by the boundary conditions.
And there are no integration constants in that solution? Because that's a non-trivial.
It's the same thing. So the set of solutions here are all related by SL2 transformations. Those are the same parameters that were in the dilaton that you mentioned.
Can always reduce to that standard canonical form with a pi t square using SL2R.
Yes, exactly.
So I know what t is as a function of u, and then from that equation I know what z is as a function of u.
Correct.
So I don't know the whole trajectory.
Exactly. Now I claim that these solutions are eternal black holes. Okay? So the fact that it starts here and ends there tells you that you have some sort of horizon. Looks like this. It looks like that.
Just for a minute, because just to connect with the past talks and so on, the other way to put it is that since he's taking a solution where T mu is 0, these are just the solutions we have discussed many times of JT gravity.
Yeah.
And there, you have this dilaton profile which has these three
Linear
parameters,
yeah.
but you can do an SL2R transformation. And then, so the dumb way to do it, another would be just solve the bulk equation which we all know of JT gravity, then locate the boundary where phi takes a constant value.
Yeah, that thing.
Because it's phi boundary. And then once you know where the boundary is, you know how proper time goes, etc. And then you can obtain the relation between
Yeah.
And this cottage t sigma is not familiar to me. I remember more simple dependencies, but that's just on SL2R.
That's actually the short cell R coordinate. This is a coordinate
between
schema.
Poincare and short.
Okay.
Exactly.
Staticness is manifest in the short.
Exactly. Lines of constant dilaton look something like this. It starts large here, goes to some value here, and then goes small as you go up. So just the way the R coordinate works in regular Schwarzschild.
So that sigma is roughly actually the R star coordinate.
Yeah, effectively, yes. Okay, so this is an eternal black hole.
I'm sorry, I'm sorry to
No,
confuse
no,
you. So
please.
But the last line is a definition of y plus minus?
Yes, you can think of it like that. Yeah. Okay. Now, so that's it for the review of JT gravity. Next is the kind of black hole I want to consider. So that's an eternal black hole.
So this is a black hole solution. In addition, there's a vacuum solution of JT gravity?
Correct.
So where in your choices did you choose to, where have I seen that you're working with a black hole? You know, somewhere when you solved the equations, you made some choice that gave me the black hole. Where was that choice? In the choice of the phi solution?
Well,
T square.
so first of all, in JT gravity, all solutions are eternal black holes.
Okay.
That's one point. What controls the size of the black hole is the T, the temperature,
Okay.
or can be thought of as this E naught. They're related.
Okay.
Okay.
So the appropriate T going to zero limit gives you the vacuum.
And in the
Yes,
language
it gives you Poincaré.
in the language of the three solutions of phi, you're making some choice in that three parameter space.
Yeah.
Yeah,
so
that's just moving this point around
Okay.
in this space.
So each SL2R invariant orbit is characterized by a value of E0, and then there's going to make a different choice.
Yeah, I suppose you could just scale U in some sense to get different. The boundary time, if you change what d by dt is, you're changing the temperature.
Well, looking at carefully in that.
I mean, it's the usual situation, right? Temperature is not well defined in a conformal field theory. It can be scaled to any value.
But this is not a conformal field theory.
Okay.
The dilettante breaks it. That's the point.
The thing you worry is that the boundary is located at a fixed value of the dilettante.
Yeah,
So
yeah,
that's
yeah.
why the-
Okay.
Yeah, there's a boundary condition. Phi goes as phi b over epsilon, or phi r, I guess, over epsilon. If you do your rescaling, you rescale this guy, so you would also rescale that guy.
Okay.
Yeah.
Thank you.
Yeah, that is why the temperature and the energy are the same thing because there is only one scale.
Well,
This T square.
because that's t squared for completeness.
So that there's a new scale which is how the dilettante varies.
And there's a phi r somewhere here, I guess. I don't know if this, yeah, I think something like that.
You know, the J parameter of S by K. whatever.
Yeah, that's in phi r.
Sorry, I'm sorry to be so good, but from the way you said it, Sandeep, it is in the choice of the three parameter solution of phi.
Yeah,
That sets the temperature.
Yeah.
that's right.
Mhm,
If you do it
mhm,
that way,
mhm,
then that,
mhm.
that is
Fine. Yes.
Yeah.
Yeah.
Basically, only one freedom is the left from that SL2R, and that one freedom corresponds to your choice of T.
Mhm.
That will.
Yeah, that was what was confusing me. I thought you said all solutions were equivalent by SL2R.
No.
all solutions for a fixed E naught
Yes.
mass.
Yeah. Okay. So the one parameter set of solutions.
Yes.
One parameter set of variables.
Yes.
Yes, which is the temperature.
Yes.
Okay. Now,
So I mean, you were thinking of all of this as embedded in the global geometry, or are you thinking of the Poincaré wedge as the
well, because I drew these regions, I'm thinking of it in the global geometry. So there are a set of coordinates that cover the entire global ADS2. And in those coordinates, you'll find that the dilettante just looks like this. I mean, if you just work in Poincaré coordinates, you only see this region. But you can work. I mean, you can work directly in the black hole coordinates or the Schwarzschild-like coordinates, and the coordinate system does this as electronic here. It covers this entire region.
The reason I asked is that if you want to consider the Poincaré wedge itself as some autonomous entity,
Mhm.
then you have to put the end of the world plane or some such complicated thing here.
No, I would just say that in that case, you've worked in a coordinate system that just doesn't see these other regions. And I mean, it's still the same state. If you put an end of the world brane, you're changing the state somehow. But also JT gravity doesn't have end of the world branes.
Yes.
So, and you can work in the Poincaré coordinates in JT gravity. So you don't actually need them. Okay. I want to consider an eternal black hole, but a slightly different kind of eternal black hole. One which is in a slightly different kind of theory. I want to do the following. So let me draw what the space-time looks like. So let me imagine that I have the same solution as I had over there, but let me include two external systems, which I call the bath, or I'm going to call this region BR and this region BL. What I have here are two CFTs of the same kind of CFT that lived in this bulk, but defined on a flat metric. Okay? So here I have a CFT on the background metric ADS2, so maybe I should just write ADS2. And here I have a CFT on the flat metric delta or eta, I guess, whatever it is. And the idea is that I want to think of the system as having, or if you want to think of the ADS theory, I want to imagine having transparent boundary conditions on the two boundaries. This is transparent only for the matter, not for the metric. So the metric is still asymptotically ADS2, as in it's still not fluctuating at infinity, but I want the matter to be able to exchange stress energy with these external systems.
And the dilaton field ends at the boundary.
The dilaton field ends on the boundary, exactly. Okay. So the metric here, I'm going to write it as, so the natural way to extend the coordinates from this region to that region is to write down, is to say that the metric here is simply dy plus dy minus. Okay. Okay, any questions about that general picture? Okay. Now let me make some statements about what the state of the CFT is on this extended spacetime. So we know that in this region, in the bulk region, we have the stress tensor in the x coordinate is 0. It's a vacuum solutions with respect to the background metric. So you need to specify when you tell me what your stress tensor is, you need to specify with respect to which metric you're computing it. And let me just, so the statement is that the stress tensor here is given by this.
Okay.
Right?
So when you say transparent boundary conditions, can I think of it this way? Up to a while factor, this space can be made sort of just flat.
Perfect, yes.
And then it's just left moving, right moving.
Exactly, that's exactly what I mean. So given the stress tensor here, we can now determine what the stress tensor is here and here, what it needs to be in order to maintain that the stress tensor vanishes in this region.
I missed that last point. What was this T plus plus X? Where is that?
This is the vacuum solution that I started with. So again, the thing that I want to have in the bulk is the eternal black hole solution.
Yes.
We know that that's a solution of the vacuum equations.
Yeah.
So I want to impose this condition everywhere in this region.
That's a condition I should think of on the matter stress tensor.
On the matter stress tensor, yes. When I say T, it's always going to be matter stress tensor.
Okay.
And I'm saying that this fixes what the stress tensor is in these two wings.
Why is it the case like, can it not be that when it is interacting, when you have made the boundary transparent, the interaction with the bath, here the bath is sort of simple because you have taken the same CFT and so on. But if the bath was complicated enough, then I would have imagined that the interaction would have changed this this matter stress tensor.
Yeah, maybe, but I'm not considering that case.
So here sort of the simplicity of the bath ensures that you can maintain this condition throughout.
Yes, yes. But you can imagine maybe, if you want to demand that the stress tensor still is equal to this exactly here, you might be able to choose the right interaction and the right state of the bath such that this is ensured.
It's a choice of the bath in some sense.
Yeah, it's a choice of the bath.
And the stress tensor is determined there by the usual conformity for wild transformation.
So the stress tensor in the bath, I'm going to write it as Ty. That is just given by something like this. It's controlled by the conformal anomaly.
Because it's a wild transformation of 0.
Precisely. It's going to look something like this. It's actually going to be, so this is for plus plus and minus minus. I just didn't write the plus plus and minus minus. It's going to be controlled entirely by the temperature of the black hole, and it's equal to a constant. Okay, so this tells you that the state that you have here in the bath is really It's one where you have a constant energy flux going in and going out for all time. Okay.
Just to point out one thing which I found very confusing when I first started studying the GT model, and which you noted in your paper with Joe many years ago, in case it confuses anyone else. What we have already here on this side is actually a black hole in ADS2, but the state of matter is in the Poincare vacuum. And it might seem very strange, because you might say you should really
Why?
take the Kruskal vacuum.
That's the same
for
thing.
an eternal black
No, but that's the same thing.
But it's the same thing.
Oh, okay, okay.
This is a very interesting, it's not true in 4D black holes, that say the analog, which is the Minkowski vacuum.
You ask me why isn't there the gas, right?
Yeah, yeah.
Outside the black hole.
Why isn't there a gas? And the point is a very interesting feature here, that the two are, Poincare and Kruskal vacuum and SL2 are related.
Yeah. There is a gas here, right? You can choose to measure what the energy density here is with respect to the y coordinate, and that's controlled by the same calculation, and it's the same
But
constant
in
temperature.
space-time, in the space-time coordinate, there's no gas.
That's right. That's right.
Why is that? Physically, I mean, it's a black hole, it has a temperature, why isn't it?
No. Sorry. What do you mean by the space-time coordinate? I mean, all these coordinates are just choices. So if you have an observer that's sort of,
It's
so
true
that's,
that a Rindler observer will see.
yeah, exactly. An observer that's, yeah. So I mean, this is the temperature that would be measured by a Rindler observer. You know, if he, does it, if you define the stress tensor with respect to the normal ordering given by his coordinates, by his proper time, then it's going to be that's the same statement as computing this stress tensor. So there really is radiation going out and falling back in, and whatever. Yeah.
But it's a slightly peculiar feature. I mean, a little counterintuitive at first sight, but anyway.
And from the point of view of the boundary, the radiation's coming, hitting the boundary and coming back, right?
In the case where there was no bath.
No, by boundary I mean bath. So, sorry, from the point of view of the bath,
Yes.
there's T++ you said is equal to T minus minus.
Yes.
So the stuff going
No.
this way,
Sorry.
and the stuff going there.
Yeah. Exactly. So you just have things doing this, and you have things doing that.
But if you're just a boundary observer, you're not losing energy. Sorry,
Oh.
a bath observer. There's as
Correct.
much coming in as going out.
Correct.
So you might think of it as reflection.
So when you want to compute more refined quantities like entanglement entropy and so on and so forth, that distinction is important.
Okay.
Okay.
I thought that what Shiraz says, that's how I was thinking of it so far, is that there's no stress tensor inside, and there's some stress tensor in the bulk. So it's like a conformal, it's like one of those boundary conformal field theory things, in which there is a boundary condition which says
No.
that the stress tensor just reflects.
No, there is stress tensor inside. There's no stress tensor with respect to the x coordinate, but there is stress tensor with respect to the y coordinate. This answer is correct here, and here, and here, and here. So there is actually stress tensor that just goes through. This is things don't. Maybe it's confusing things that I drew this as a solid line.
I mean, okay. If you think it's more natural to be a Poincare observer, there is not any such thing as a natural observer, but if you think it's more natural to be a Poincare observer inside and a Minkowski observer outside, then it's true that you won't see any particles inside, but the same state will result in your seeing the particle outside. But it's the typical thing.
Sure. Yeah. Okay. Okay. So something that's going to be important for us, which I guess touches on what I just said to Shiraz, which is that it's important to know sort of what the global state is of the quantum fields. And basically, the global state here, I mean that the one defined on this entire region that goes from one infinity all the way to the other. So,
Just to ask people. No, please.
No, I mean, I mean, when you say that the stress tensor is 0 or not in the bulk, depending on how you view it,
yes?
the stress tensor is a tensor. So a coordinate transformation can't change that it's 0. A Weyl transformation can.
Yep.
But I mean, just to say, if you
Yeah.
say it is. Don't do Weyl transformations, then it's just 0.
So let me define a coordinate system, W plus minus, which covers the entire patch, the entire space-time. So it looks something like this. The claim is that we have the CFT vacuum with respect to these coordinates. Basically, W, the stress tensor in the W coordinate is 0 with respect to the metric. Okay? I think I'm emphasizing your point.
No, I'm getting really confused. I thought it should be 0 with respect to in the Weyl frame in which you had ADX.
Ah, good. But the ADS Weyl transformation is simple enough that it does not pick up a conformal anomaly. Right? The conformal anomaly looks something like this. It's like d plus omega divided by omega, where this thing is equal to omega to the minus 2 dx plus dx minus. Act to d plus twice on that gives you 0. I'll just leave it up there.
And in this language, the boundary Weyl frame, it's not just getting rid of the x's, it's something more.
Correct. You mean the bath when you said boundary?
That's right.
Yeah.
Yeah. Okay, fair. Thank you.
Okay, so I claim that the state we have is the vacuum with respect to the W coordinates on the slat metric. I'll give more arguments to why that is the case. And the idea, yeah, I'll get to that.
What is the W coordinate you mean? So in the ADS2 region.
So yeah, so let me.
There's a Y factor, right? I mean.
But he's saying no,
Let me
Schwarzschild
see.
vanishes with that transformation.
No, but I'm just saying the metric is not exactly flat in the inside region, right?
Yeah.
Let me first define this state. Okay, so I define a state where it's the vacuum with respect to the W coordinate and this background metric. Now there are conditions. There's a transformation between the W and the X and the W and the Y. These transformations must be such that they give me back this stress tensor that we had over here. So for example, we know that it has to be 0 in the ADS2 region. So this means that the transformation between W and X must be some Weyl transformation. Maybe it's not worth writing the pluses and minuses. It's going to look something like this. 1 over t over x minus plus 1 over t. So the transformation between W and X is going to be an SL2 transformation. That's why this 0 stress tensor maps to 0 stress tensor in the ADS2 region. And it's going to be something more complicated with respect to the Y. Basically, you just plug in for these x's as tan hyperbolic or whatever. And so it's not an SL2 transformation, and that's why, and you generate back the same thing here. So notice that if you transform x via an SL2 transformation, that does nothing, that just replaces x to W, and then you get the same answer.
This is the part of the black hole, not the bath. For the bath, you have a different
No.
transformation.
Yeah. For the bath, it's where you replace x with tan hyperbolic y.
Sorry, I'm still confused. But it's not as if this coordinate transformation converts ADS2 to flat.
Good.
So
It's this.
you-
You need to do this and the proper Weyl transformation.
Okay, so just making sure.
Yeah,
Yes.
but the Weyl transformation is trivial.
Yeah, I got it.
Yeah.
Fine.
Good.
And then just you can, this can be for later, but just to say, at the back of your mind, is this a cartoon for the following interesting situation, which is that you might have an extremal or a near extremal
Yes,
for
yes.
an asymptotically flat space,
Yes.
and then you're getting rid of the boring transition region.
Yeah,
just gluing
this-
the flat.
This is like a near extremal black hole with a sharp neck. That's how I want to think about it. And some of the things I'm going to mention today are going to be very disturbing from that aspect. As in,
Short neck because you reach boundary infinite time.
maybe that's the way of saying it, but as in it's ADS2, then suddenly it's flat. That's what I meant.
I mean,
That's another way of saying it, I guess. Okay. All right. So the way I want to think of the state, as was mentioned a few minutes ago, as the Hartle-Hawking state generated by Euclidean path integral on the lower half of the Euclidean, so this hybrid black hole slash flat bath system. So this thing can be prepared in the following way. Oops. I mean, there's an, okay, but let me draw a singularity. There's no singularity. The idea is that here we have flat space, and here we have just Euclidean ADS2. Okay? And we're evaluating the CFT path integral on this half Euclidean space, and that prepares for us a state here.
In W coordinates, is it not just take this arithmetic and then do the path integral up in the lower half plane?
In the W coordinate, the claims that these two things are the same thing. Yeah, because okay, roughly speaking, because of this observation that the ADS2 Val transformation doesn't do anything, when you define the path integral here, you can just transform away the term that comes from the ADS2 region. It doesn't really affect the path integral, is what I'm saying.
so
You don't get an anomaly piece.
I mean, I think I understand the left-hand side diagram, which is that we do the path integral in Euclidean space in the usual way to generate the state
Yeah.
on that slice. But now on the right-hand side, you literally do it in the flat case and then tag on the required conformal factor at the end of the day. Is it? That's all I think. Okay.
Yeah,
Just to
yeah,
make
yeah,
sure.
yeah, yeah,
But
yeah, yeah.
what happens at the bottom? I mean, in normal, if you're in one higher dimension, the end of that thing shrinks to nothing, right? The boundary is.
This is not a boundary. The reason why it looks like a hemisphere or a semicircle or half disk is because I've done this point and this point are actually infinity, right? If I need to send these all the way out. So this is really just a half space
But in
Euclidean.
the W coordinate, it really is a boundary.
No, no, no. In the W, so I didn't mention this, but W really goes from minus infinity to infinity. Yeah, yeah.
So it's all of the
Just-
usual thing.
Just the usual thing, exactly. So this prepares for us the usual Hartle-Hawking state, which means that so we can do the decomposition. I guess let me work here. We can do the decomposition into Rindler modes. Yes.
Sorry, could I ask? Suppose you were doing you didn't have this complicated other conformal field theory. You were just doing this Hartle-Hawking path integral for the ADS.
Ah, good. Okay. Yes. Yes.
Then there would be a boundary.
yes.
And what would
Then-
you do there?
Then you're preparing a CFT on a strip.
And what would boundary conditions you put in the
So
boundary?
usually, then the nicest thing is to say you have Cardy boundary conditions.
But that's a choice.
That's a choice.
Okay. So Hartle-Hawking is less well defined in ADS2 than any other ADS.
Where do you say that?
Well, no. So even in any other ADS, you also have. Well,
It
I mean, there is a
closes
boundary.
No, disconnected versus connected boundary.
No, no. We're talking about bulk field theory, right? This is a bulk CFT. If you put a bulk CFT in higher dimensions, you also need to define it with some boundary.
No, but the Euclidean ADS is a half ball, right? It doesn't.
Right? You have something like this.
Okay, I see. You said there's always.
There's always a boundary.
This is for the matter coupled to the gravity.
Yes.
For matter.
Exactly.
Right.
There's no boundary for the boundary matter. Yeah. Okay. So this is just the so we just have the vacuum, the W vacuum, which we are allowed to decompose in terms of Rindler modes, And so we just have the usual. So the Hawking radiation in this case is simply Unruh radiation, right? So we just have, the usual picture. You have modes here, entangled with modes there, and they're entangled across the future horizons. The state of so here we have the statement that I just made is the following: that the omega vacuum or W vacuum it can be written in terms of the Rindler modes in the following way. Some Hy is the boost Hamiltonian. It is the Hamiltonian with respect to the y coordinates. So H evolves you along these lines. And if we have a free field, then we can further write this as the usual thing in terms of modes and E to, roughly speaking, beta over 2 and omega and L and R. Okay, this is just the usual thing. This beta here is the same as the temperature that we had. So it's 1 over T. Because it follows from the coordinate transformation, which has a temperature in it. Okay, now this, so the idea now is that you should think of this as a toy model for, as Sandeep was saying, as for charged or rotating black holes in asymptotically flat space in any dimension, where the neck transition is sharp. So usually we draw something like this. But now have something like this, effectively. So again, this is a toy model for that. But I claim that more generally, the observations I'm going to talk about regarding the system, I think apply to any eternal black hole in any number of dimensions, including the standard maximally extended flat space Schwarzschild black hole. And some of these observations were actually made by Samir Mathur in a paper maybe 2 or 3 years ago that were not appreciated by the community. But the claim is the following: that the eternal black hole, so he didn't make all of these claims, he made a few of them. So the eternal black hole has a Hawking information paradox, the usual information paradox, not the Maldacena information paradox. And it has a Hayden-Preskel protocol, and it has, so therefore it requires complementarity, and it also has a firewall paradox. Okay, so
You will have to explain some of that to us.
I will definitely. I don't think I'll be allowed to leave alive without explaining that to you.
This is the flat space eternal black hole.
Flat
Is it
space.
also true for the ADS eternal black hole?
No, it's not.
When you say this chart making this picture, the math part here is coming from the rest of the ADS code?
Yeah, you can think of it like that. Sorry.
Even if it is small in ADS, even if it is small enough?
Well, I'm imagining it. It has to be big enough because it has to be stable, I guess, maybe. Yeah. Okay. So that's okay. So let me begin. So we're done with this. Let me begin briefly by briefly reviewing the information paradox.
So what is the limit to which this sharpness happens?
Oh, I don't know. I don't know if it's a controlled limit. Like if we can actually, if there's a parameter here that can take it to that. Yeah. So it should be thought of as a toy model for this. Okay. Okay. So let's start with the information paradox. Let me begin by phrasing it in the usual way that it's described. So we consider a black hole. I don't care about the asymptotics. It's formed from some matter in the state psi m, and then it radiates. And the exterior Hawking radiation is entangled with the interior Hawking radiation, and the density matrix of the exterior radiation is some thermal density matrix. Okay, So we have a process, and then the black hole evaporates away completely. And so it seems like we have a process that takes you from a pure state to a thermal state, so pure state to a mixed state. So this is the problem. Unitary evolution in quantum mechanics does not allow such things to happen. The essence of the paradox is captured by the evolution of entropy, of various notions of entropy. The first is the fine-grained entropy of the radiation. So it does something like this. It grows until it asymptotes to some value. So this is S radiation, which is just trace minus trace rho log rho of the radiation. The second notion of entropy to plot is what is called the coarse-grained entropy of the black hole, which is simply the Bekenstein-Hawking entropy. This coarse-grained entropy, it's given by the area of the horizon as it gets smaller and smaller. And it should be thought of as a measure of the size or the dimension of the black hole Hilbert space. And therefore, we have a paradox, not when the radiation evaporates away completely, going from this pure state to a mixed state, but rather right after, we get a paradox as soon as the fine-grained entropy between the black hole, the entanglement entropy between the black hole and the radiation is larger than the coarse-grained entropy of the black hole. Because it seems to say that the black hole, that entanglement is much more than what the black hole has room for. Okay.
So this comes from the fact that the entanglement entropy of the external system with some given system is bounded by the log of the dimension.
Precisely, exactly. Now I claim that this exact same issue arises for the eternal black hole. Okay? So,
Sorry, just to say, if you were to plot the coarse-grained entropy of the radiation, according to Hawking, it would basically track the curve.
it's this thing, yeah.
That's one way to look at it.
Yes. So that's what. That's actually a calculation that was done prior to these set of works. No, sorry, and also your work. Yeah.
That was fine-grained in the semi-classical approximation.
The statement I was making is that Page and Hawking and friends, the way they computed the way that they actually computed the entropy of the radiation is to compute the coarse-grained entropy of the radiation and say that, oh, it's a thermal state, and therefore its density matrix is thermal, and therefore the fine-grained entropy should be equal to that. What you guys did in 2 dimensions was that you computed it exactly, although there's a mistake, but I'll get to that later. So it's a different calculation, but I think it lands on the same answer.
But it's really trace rho log rho.
Yes.
Anyway.
Exactly.
I was just saying Hawking's calculation is actually, in a sense, the coarse-grained.
Yes.
And sorry, just to make sure, in your setup, what we mean by trace rho log rho is very well defined. There's this Hilbert space for the bath, and you can compute its entanglement entropy.
Yes.
Now, in a black hole in flat space, what exactly do we mean by rho radiation? Can you give a precise definition of that at Scribe class, for instance?
So one proposal is something I'm going to mention in a page. So let me address that later. Okay.
Sorry, we should wait, but roughly, although you can't quite make it, I think so far totally precise, if you could make entanglement precise in a theory of at least asymptotic gravity or whatever, then you march up on Scribe class.
Ultimately, that's what you have to do.
Yeah, and you're using the fact that basically gravity is free of Scribe class. So it behaves, somehow there's the statement that it behaves like a just free quantum field theory. You forget that it's gravity, and you define it.
There's some vestiges of it being gauge theory, but you more or less get a imbalance.
Okay. So I claim this issue arises in the eternal black hole. So maybe I should draw it here.
Sorry. Just in flat space, all these soft modes that we keep hearing about, that doesn't play a complicating role.
I don't see what I don't see what they play.
Okay.
What they do.
Let's say that there has to be a more precise definition of entanglement. in gauge theories, it is more tricky, and some of the issues are not there. I think probably won't in the end affect the issue.
Yeah, I don't think so.
Yeah, it's open.
Okay, so let's say we want to compute the entropy of the radiation. So that's like, let's say at t equals 0, that's like computing the entropy of the union of these two regions. Let me, okay, so the thing that we want to do is understand how the entropy grows as a function of time on both sides. Okay, so we take these 2 points and we evolve them upwards in this fashion. And the claim is that this entropy grows linearly with time. And I'm going to give you 2 arguments. The first, which is a schematic argument, and then I'll give you a more precise statement.
Even though the black hole entropy never changes. The cosmic black hole.
Yeah, exactly. The Coarse-grained entropy doesn't change. This space-time is static, right? The horizon area is fixed.
Sorry, this is now, you have transparent boundaries in this picture?
Yeah.
Okay, you have transparent boundaries, and what are these 2 lines that you have?
I'm going to compute the entropy of the union of BL, BR. This union, this thing is BL and this thing is BR. It's a space-like slice of BL, BR.
Time slice, at a given time, you can have space-like slice on both the baths, left and right, and
Yes.
you want to compute
I'm
entropy of the union,
Of the union as a function of moving this point upwards.
which is the different times.
Yes. So these are, yeah, exactly. So time goes on.
Entanglement entropy of the 2 baths as a function of time.
Yes.
Yeah.
Just so I make sure, I'm sorry I put it like this, just to.
Yeah, please.
You really mean the entanglement in the radiation of the bath computed using the usual formula in 1 + 1d CFT, right?
But I'll get, yeah,
Okay.
I'll get to that.
That increases.
Yes.
In this situation.
Let me give you a schematic argument to see why it should increase. So we have Hawking radiation here. This let's consider a mode here. So I'm using free field intuition. So I have a mode that's going out like this. This mode is entangled with a partner mode like that. And also on the other side, we have the same thing. This mode is entangled with a partner mode like that. Notice how when I went from this slice to this slice, I captured this extra mode. And then
Say that again, which was the,
going from this is t equals 0.
you
I captured this. So I captured this. So I have to count its entanglement with its partner behind the horizon. And the same thing happens on the other side. Going from here to here, I capture this, which is entangled with that. And this just keeps happening.
And it's actually true in that formula where you have the interval with the cutoffs and all that.
I'm going to do it right now. I'm going to do that calculation right now. And so this, and this keeps growing at the same rate. So it's controlled by how fast these quanta are going from the bulk into the bath, and that's controlled by the temperature of the black hole. And so the claim is that we should find that S should should go as time, linear in time, controlled by the temperature, and also should be multiplied by the central charge of the theory that we have, of the bulk matter theory. Okay.
I did not understand, why does this argument suggest that it has to be linear and not some other?
Because the rate is the same for all time.
Is there exponential connection between crustal coming in the cutoff changing? Okay, anyway, go ahead.
Yeah, that's exactly what it is.
That's
Yeah,
what
it comes from how the cutoff changes from W to Y.
Yeah, now that you say it, it's I never
Yeah.
realized this.
But no, but if you consider one side,
Yeah.
just do this, it doesn't change with time. The reason being is that so we got the entanglement between this guy and this guy, but we lost the entanglement of this guy. Sorry, there's a mode like this. That was entangled with something like that. Exactly. There are things coming in and going out. But the things that are coming in, they get captured by this guy. That's why. So, and also this thing had to be constant because of boost invariance. But here we don't have boost invariance, so it didn't have to be constant.
So if the subregion was finite, then you would have linear and saturation. But now the subregion here is infinite, so you don't have a saturation. You know, this process ends after some time. So you have.
Let me get back to that. So from the argument that I just gave, it looks like it has to keep growing indefinitely.
Yeah.
Okay.
If you had just one side, not the other, then which modes are missing? Which entanglements we are
Okay.
lost?
Let me draw it. So here, this mode is entangled with this mode. Which one do I want? Oh, I drew this one wrong, but whatever.
So
Entangled with this mode.
the earlier was supposed to be slightly above.
Yeah, this one was supposed to be somewhere here, I guess.
Okay, now this is what we are losing, but now this is captured by the left boundary.
Yeah, but I'm saying if we just compute the entropy of the right,
It will remain constant.
then it's going to remain constant because you lose one, and you gain one. Yeah, but it gets captured by the other side, and that's why it doesn't. Okay, so let's check this explicitly and just compute the entropy of the union of the baths using just standard CFT techniques. The idea is that we have the W vacuum, right? So we have the W vacuum, and so therefore the entropy of the union of BL, BR is simply given by the usual formula, C over 3 log W1 plus, these are the endpoints, W2 plus, W1 minus, W2 minus, divided by 4, epsilon 1W, epsilon 2W, and which then must be expressed in terms of the physical bath coordinates, the W plus minus. By that I mean we need to transform these guys and also transform the coordinates, the cutoffs. The cutoff transformation comes from the following identification. Well, it just comes from the metric. This thing is equal to minus. We simply express this metric in terms of the W metric. The statement is that this is should be thought of as the Y cutoff. So this thing is epsilon Y squared, and this thing is epsilon W squared. So now we just need to write epsilon W in terms of Y. And so we get these factors in the entropy.
W1 and W2 are the endpoint. Those points
Yes,
there,
yes. So W1 and W2 are these 2 points here,
which keep moving.
Exactly.
And the point is that even though we are interested in derivative of entanglement entropy, we cannot forget the cutoffs because cutoffs has a time dependence.
Yeah, exactly.
Otherwise, usually we could forget about it if it is
Exactly. And so putting all this together, you'll find the entropy is just C over 3 times the log of cosh squared pi t times 2u divided by 4 pi squared t squared epsilon y at 1, epsilon y at 2, which at late times, u is I should have mentioned. I guess I've been using u for physical bath time, proper bath time. So this is at late times, this is an exponential. So this is just 4 pi over 3 times c times t plus terms which go as the logarithm of the cutoff. Okay? So we got the linear growth piece. So maybe this might address what Shiraz was pointing out before, that to get the entropy of the Hawking radiation, something you can do is subtract out the vacuum answer, subtract out the t equals 0 answer. What that will do is that it's going to get rid of the cutoff dependence. Okay? So that gives you the growth of the entropy due to the Hawking radiation. And so it seems like what we have is the following picture.
Sorry, just not that it's so important, but the W coordinates were going off to infinity at asymptotic infinities.
That's right. That's right.
Okay. Sorry, no, this is so much. Okay.
That's right.
Can I ask a remedial question?
Yes.
If I have a conformal field theory and I have an interval, I compute its entanglement entropy, does it change under a Weil transformation?
Yes.
Precisely because what Indranil was mentioning, that
The cutoffs.
the cutoffs.
It's the same statement here.
The cutoff which appears is in the affine parameter in which the state is in the vacuum. It depends on
Yeah, you're changing proper distances, so you change the cutoff.
Yeah.
Okay. So now, let's plot what this entropy looks like. So the entropy simply grows with time, linearly. Starts at some finite value at t equals 0. So this is S radiation. But we can also plot the coarse-grained entropy of the black hole, as measured sort of near the two boundaries. That's just
An amazingly simple case.
yeah, exactly, and it's just a constant. And this is the coarse-grained entropy. I guess let me just write S Bekenstein-Hawking. No. I should write S coarse, which is equal to 2 times S Bekenstein-Hawking. I guess depends on what you mean by the Bekenstein-Hawking entropy for a wormhole.
Because it's two-sided.
Exactly. So yeah, okay. So maybe I should not put the 2, as I was just yelled at. So this is just twice the dilaton at the horizon divided by 4 g Newton. Okay, and there you go. We have this overfilling paradox. It seems like the black hole is more entangled with the radiation than it has room for. And good. And we run into a paradox. So you can ask, at what is this time here? So this is the page time. This time, you can just equate this with the Bekenstein-Hawking entropy. And it happens when time is beta times S black hole divided by the central charge C. So it's the usual thing. So this is just a page time. This is how it's usually phrased.
Did Samir Mathur also work it out in 1+1 dimensions?
No. His argument was it was a lot more coarse than this. I actually didn't read that paper. I just looked at the pictures and I saw something that looked like this. Okay. But yeah.
One guy keeps going and one guy is roughly constant, and you will have a time.
Yeah.
Yeah, but here, the really nice thing about this is, I mean, these kind of arguments sometimes go wrong.
Yes.
So this is a calculation.
Yeah. Okay.
This kind of calculation can be done in higher dimensions.
Just to
Yes.
How?
Well.
much harder.
So in higher dimensions, it's the same. Let me try to argue it.
In principle, I think.
So let me first say the less precise statement. So let's say this is just a usual flat space Schwarzschild, and we consider two constant R surfaces which are very close to the horizon, and then we can imagine. So we can do this schematic argument, right? We have Hawking radiation coming out. So we want to compute the entropy of this region as a function of time. This schematic argument applies. Okay, and so we can.
Effective field theory approximate?
Yes. I'm working in the semi-classical limit. I have a fixed background, and I'm just computing the entropy of the quantum fields of the union of these two regions as a function of time.
I can see the schematic, but to try and make it precise, I think is more tricky there because the entanglement is dominated by the area term.
No, I'm computing I'm computing the field theory entropy.
Even the field theory entanglement is dominated by the area term at the boundary, So
I think that's just a cutoff piece. That's a constant in time.
Here also, the dominant effect is due to the cutoff. It's just a log. And the crucial point is that the cutoff should be in affine parameters, but has to be stated in physical terms.
No, but we agree that that's a time-independent piece.
No, but I'm saying the time dependence crept in because it was actually the cutoff in affine.
No. I think that's because of the trick that we use to compute the entropy.
Okay.
But if stated physically, and you say you have a cutoff, you work directly with the physical coordinates. You have a cutoff dependent piece, which is independent of time.
Yeah, but I'm just saying, okay, since the origins are tied to that, you'd be a little careful.
The
if you
counter
don't-
terms have to be chosen carefully,
Yeah,
including curvature
you
terms.
make sure that you understand all that precisely.
Okay,
in that
okay,
is what
okay.
I'm saying.
Okay.
So, I mean, I understand the schematic diagram, I'm just saying.
But
And
there also
I-
you would have the same type of setting where you have this bath CFT glued in
Every time when you are
on the
talking
boundary.
about-
So in which setting? So here? I mean, here I don't have that, right? I mean, this is just a regular Schwarzschild black hole in any number of dimensions.
I see. But then
But
you
this
want to use this conform field theory formula.
No. We don't want to use the conformal field theory formula. We want to use whatever appropriate formula is to use here.
Sorry?
We want to use whatever appropriate formula is in this context, which is some. I mean, I've never done a calculation of entropy in higher than 2
No,
dimensions.
but there also you could build up such a setting, right, where you have bath CFT glued in.
Oh yeah, definitely. Yeah. You can. But I want to make a statement about just regular Schwarzschild. And I say the same schematic argument applies there. And in fact, so again, this is also not very sharp, but again, okay, maybe this also relies on the schematic argument. The Bekenstein bound is violated, right? So because we have a lot of Hawking quanta inside, which are entangled with the quanta outside. So it seems like the amount of entanglement entropy inside the black hole, behind the horizon, increases arbitrarily large.
I just wanted to say no, you're right, absolutely right. I just wanted to say one small thing, I'm sorry, but harking back to the old days, which is, the kind of, you were saying, did anyone do it for the eternal? Well, what we have done is to do a single-sided black hole, but to feed it pure radiation at the same rate at which it evaporated.
Yeah.
In effect, keeping the
Yeah.
black hole entropy fixed and then seeing this growth. But I think this is even, crisper in a
Yeah.
sense,
Yeah.
right? Because it's just the eternal. But you're right, here also you can similarly just feed it
Yeah, or just consider this. Yeah.
So in high dimension, your matter must include gravitons, right? That's an additional. I mean, here there are no gravitons. The
But-
only thing that gravity does is to take care of. I mean, you just take care of all the gravity stuff by Fourier transformation.
This is the formula for the entanglement of the vacuum, right?
This is the vacuum entanglement entropy of a CFT in 1 + 1 dimensions.
So the solution is going to be that it's not a vacuum state.
There's some solution that, kind of.
But what the bulk really seems to suggest is that it's because the cutoff in affine coordinates is getting smaller and smaller compared to the Planck scale. This calculation is yielding a bigger and bigger entanglement. It's really the ultra-short modes, hugely correlated across the horizon, which carry their entropy.
But that's just I think that's just a coordinate artifact.
But I mean, physically also,
I mean, that's just because we're scrunched up here and so on.
yeah, but I'm just saying, this is just saying in words what is also usually people would say. It is, if you want quanta of some fixed temperature as seen far away, later and later.
You're just saying they come out from the cutoff
They come
here
out
near sort of behind the stretched horizon or something.
Yeah.
Yeah, sure, but that's just a.
No, it's a state, but I'm just, again, drawing attention here, which comes out here, which is that makes it clear it's really a Transplanckian type of issue in the sense it's ultra-short modes.
Yeah.
Of course, they are vacuum.
Exactly.
Of course,
Exactly.
they're vacuum, but it's
Exactly.
really those modes which are carrying the entanglement. And I'm saying this because when you go ahead and you propose your solution, the question may be whether the GT model you're starting with is a consistent theory at those ultra-short Planckian.
Let's defer that to later. Let's defer. Okay.
Right.
Same kind of objection.
Okay. Let's defer that to when I get to it.
Yes.
Okay. So this is bad. Why is this bad? so the usual arguments are, this seems to say that we can have objects in a theory of gravity with an arbitrary number of states at a given fixed mass. You know, if this was indeed the correct answer. And then, you know, so these are often called remnants. And you know, the usual argument is that such a possibility is experimentally ruled out by, you know, particle physics experiments because they can run in scattering amplitudes and so they run in loops because everything couples to gravity and gravity couples to this. So no matter how small the coupling is, if you have an infinite number of states, you will pollute scattering amplitudes. Yes.
Wait, but don't you just have a paradox in quantum field
Yeah,
theory in curved space? Look at
why?
quantum field theory on this black hole background.
Yes.
Gravity is not allowed to be dynamical. You
Let's say.
generated your paradox.
Why is that a paradox? Why so? But there's no. Why is this a paradox?
Because your entropy is increasing.
No, but in quantum field theory, entropy can increase.
You're saying it's because
Is the sum of
it's if you take the whole slice, it will.
Yeah, exactly. The whole slice is zero, pure.
Just to put it another way, that limit, Shiraz, you're saying, where gravity is not dynamical,
Yes.
is implying going to infinity.
That's like taking
And
this
then
thing to
S
infinity.
black hole goes to infinity.
Yeah.
I see. But suppose if I asked how, I suppose this is a question of cutoffs. But if I asked how much space there was in the Hilbert space, I suppose it's infinite.
Yeah, exactly.
Yeah.
That's the issue.
Yeah.
Okay, so now
What you said before that the entanglement is becoming larger than the Hilbert space.
that's my second point, which is that this is not consistent with. I'm trying to make a precise statement about this model. This is not consistent with ADS-CFT. Here I'm imagining. One can imagine that this bulk system is actually is dual to two quantum mechanical systems. So you can imagine that this thing is actually can be redrawn in the following way. So this is BL, this is BR, this is L, this is R, two quantum mechanical systems, which are in some sense dual to the JT gravity with the bulk CFT. And we know, in the usual way the holography works, so this quantum mechanical system has a finite number of states below any energy. And so this is inconsistent with the density of states that we expect for holographic systems and really for any quantum mechanical system or any. Let me just put it as that. At that.
Just repeat the statement again. Just the last thing.
Yeah. So it is not. So when we have a holographic CFT, then we know that the density of states is finite below any given energy. And this is not consistent with that.
But I was trying to think within that language, but I was getting confused by the fact you're not moving along some. I mean, is it clear energy is relevant? Since you're not.
The energy is constant. That's what I'm using. The energy of LR is constant. Yeah. Yes. And so this means that what we should actually get for the.
Because the energy of L and the energy of R are both constant.
Exactly.
Though you're not looking at the thing with the d by dt conserved.
Even if I do that, the energy. It's constant for any time evolution.
It's constant
Separately,
and
precisely.
And therefore it's constant.
Yes, exactly. So now you should. Okay, so what is that? Okay, so this.
And this so I'm sorry.
Please.
But this requires you to use ADS-CFT. It's not some bulk
Yes.
argument.
Well, I mean.
Because in the bulk,
So-
the thing that's conjugate to d by dt is constant. But that's the boost thing, right? That would require you to take one guy up here and one guy
No,
down.
sorry, but I mean, hand-wavingly, I mean, there is a notion in the bulk, right? I mean, for an observer that's following this trajectory or that trajectory, they still feel a black hole of some given fixed mass.
Yeah. In the eternal situation, separately the masses can be measured by the fall-off.
Or said differently, the Bondi mass is fixed on both sides, as measured at infinity.
What's the conserved charge? Does conserved charge conjugate to d by dt? requires you to go up here and down there, right?
Two different concepts, right and left. The ones that are measured
Exactly.
are different ones.
Exactly. They're separately conserved in this case.
Well, if you've got a background that violates this,
Well,
I mean, there's only one isometry.
I'm not trying to find an isometry. I guess maybe that's what I'm trying to say.
Yeah, but I
Okay, the ADM energy measured at infinity here or there is a fixed thing. But this is why I wanted to use Bondi mass. There's a notion of mass that you can measure at future Scri plus, and that's also fixed for any time here or any time there.
Okay. No, I agree.
Yeah.
The constraint equations at the end of your ADS tell you that stress tensor is conserved here and there.
Yeah. But it's also true in flat space, is what I'm saying.
It is true that to the extent this is a caricature of an asymptotically flat situation where you've taken the neck region, there might not be a very, there'll be one precise definition of total mass at asymptotic infinity.
Yeah.
There probably won't be a very precise notion on just the ADS region if it's coupled to the asymptotically flat region. Once you have that coupled, then I don't think it'll be totally precise.
No, but even here there's a.
I mean, certainly.
Oh, I see what you mean. Well, sorry. In this, so are we still talking about this case about ADS glued to flat space?
Yeah.
Then we don't need to define energy there. We can just define energy on the boundary, which we can do.
We can, but
And
I'm
it's
saying to the extent it was a caricature, so the worry here is once you include their interactions with the bath weather,
Why should it be conserved?
there's a very defined quantity. That's what I'm
No,
not sure about.
but I'm saying we can work directly with the eternal black hole in asymptotically flat space without this model. And I'm saying even here, you have a conserved. You can compute the Bondi mass at future Scri plus, and that's constant separately here and there.
Why is Bondi mass? Bondi mass usually can change when there's radiation. Bondi mass is usually not constant.
In the eternal black hole space-time, it's not constant.
No, I'm saying.
I-
It's not a constant.
Oh yeah, definitely. I agree. But I mean, this didn't have to be constant. We're just considering a state where I'm claiming that it might be constant. Although I'm actually not clear, sure, because you have radiation
Yeah.
coming out.
I mean, I was only making this statement vis-a-vis the comment that energy of E plus R
Yeah.
is fixed.
Yeah, it's not very clear.
Yeah.
Because the energy leaks into the bath.
Yeah, that's why I was.
Yeah, it's not so clear.
I think the flux going to future Scri plus is constant. I think that's an indication that the black hole mass is the same. It's fixed for all time. The
yeah.
flux, there's some stress energy flux going out into Scri plus.
Yes. And you're saying that is constant, and therefore the black hole better not be changing, otherwise it will be radiating at different rates.
Exactly.
That's your point.
That's my point.
But your left and right boundaries here doesn't map to this constant R slices in this picture. So you want to argue for the constant R slices in that?
No. We just wanted a.
Here you try to argue that in L and R this is constant, right? So if you don't want to.
Let me see. Actually, I'm forgetting the goal was of
I
discussion.
mean, I guess Ahmed might just say that in the eternal case, what he wants to claim is that the black hole mass stays the same as time goes by.
Yeah.
There's a good definition of each on each side. Of that
Separately,
mass.
yes.
Because you can look at asymptotic infinity and
Yeah.
Newton's
Also-
law on each side.
Also,
And
you.
then that's enough for him to say that, look, the black hole entropy is not going to change.
Exactly. Or we can just say it's the size of the horizon, right?
Or the size of the horizon. You
Yeah.
can make orbits of planets on both sides going around you.
Yeah, exactly. Okay, so what should the entropy of the radiation look like as a function of time, assuming that the theory is unitary? This was analyzed by Page, and the result is that it should actually, for the first part of the black hole lifetime, it should follow the coarse-grained entropy of the radiation as close as possible, basically saying that the entropy should grow as fast as it possibly can. But then once it gets to the Page time, empty page. It should transition to the coarse grain entropy, basically because the black hole doesn't have more room to carry more entropy at that energy. So this is the page curve for this context. And the goal is to reproduce this page curve. And the claim, if you somehow manage to reproduce the page curve for both systems, for the radiation and for a suitable definition for the entropy of the black hole, which in this case is going to be the entropy of LR, we can talk about that later, then that is tantamount to resolving the information paradox. Right?
Okay, Ahmed, I'll say one thing. I think Abhi, you teach at 11:30?
Yeah, but you guys should continue.
No, I think it's not. Yeah, so I think if you don't mind at 11:30, what's the point?
But I think someone will come to ask for the room also.
Yeah.
Okay.
So maybe in 2 or 3 minutes.
Okay, but I think this is a good place to stop actually, because the next set of things I was going to talk about is the Hayden-Preskel protocol, then black hole complementarity, then the firewall paradox, and then you guys are going to try to kill me. That's it.
You need a 4th lecture.
At the rate,
Suggesting that actually.
maybe.
What is your? When do you teach?
11:30
On Friday?
on Friday. Yeah.
Thursday?
Thursday is tomorrow.
Did we want to have another lecture today?
The problem is that we have distinguished people in our.
How about tomorrow starting from 10 onwards?
Yeah.
That's a
I'm.
So we can try to find some room here.
Is this room available when G66 is not available?
How about
We'll find a room. We'll just have to tell couple and get it recorded. That's all. Somehow we'll find it. Let's say that. Let's say 10 o'clock tomorrow.
You know, there's that room in the stores. That's always available.
we don't have to stream to ICTS.
Yeah.
We don't need that. We don't need that.
You know, frankly speaking, math seminar room is never used. We just walk in there. They never give it to us, but when you go in this, never.
So let's plan to start at 10 tomorrow. I think that's something. But we'll find a room. So
Yeah.
if you send an email, sure. So anyway, let's thank him. It was a very, very beautiful Q&A.
Oh, thanks.
Thank you very, very much.
I think that was facilitated by the simplicity of the model. We're really shocked at how simple this is, and it has all these nice effects.
It's also very, very beautiful.
It's like magic. I mean, if you had some other matter, the thing would be the same. Conclusion would be the same, right? Instead of conformal matter, let's say there's some massive something put in here. I mean,
It should be massive. It should fall back into the black hole. That's something. It should not. So it needs to be massless because I want the radiation to go away, to reach scribe plus. If it was massive, it'll fall back in. Yeah, modulo that, the CFT is just a trick to be able to make these computations. But
Not to take anything away from him with beautiful calculation, but these at this level, not the subsequent work that Ahmed has done, which he'll describe, but these calculations were done already in the context of the CGHS models. This is a little bit different where you can feed it and keep it, and so.
you can also do that here. We also consider that case as well.
But it's true that the 1 + 1D situation affords a very simple context and suggests a possible resolution in the context of now ADC. So, yeah, wow.
Just one question. If you could make the contribution to entanglement and to be precise from which energies it is getting the contribution, do you expect that this argument that the main contribution is coming from the cutoff will sort of tell you that the leading correct, the one that gave you the linear growth, this is coming from the high energies?
It is coming from, okay, let me say 2 things. One, the reason why it comes from the cutoff is just because, I mean, that's an artifact of the calculation that we made, or that we performed. That's my first point. So we should not worry too much about that. But let me make my other comment, is that yes, in a sense, it is because of radiation coming from sort of modes that are closer and closer to the black hole horizon. So in that sense, it's.
That's reflected directly there.
Yeah,
No,
but I mean, but I don't know how worried we should be about this, because whether they're very, how close they are to the horizon is a boost related, it's a boost dependent statement, and so on, and.
Well, I mean, the proper momentum or wavelength is extremely short.
But with this,
If they're going to make their way out at late time and be of order the temperature.
no, but
That's
that, no, but
a
that,
sort of
but that
a
depends.
various-
No, but that depends on your, on which frame you're working in.
Well,
I can
if
boost
you
this thing to
take-
make it look like it's there.
Okay, let's put it like this. If you take any nice infalling frame,
Nice. Okay, what's nice?
freely falling, any freely falling frame,
Yes.
and in that frame measure the wavelength of quanta that will make their way out, they'll be extremely small.
I think I disagree. I mean, I can have this freely infalling frame, which is very boosted.
If you have
Then with respect to this guy, these modes here, which look like very close to the horizon.
Guys, no, not those. No. Sorry, allow
I-
me. That is, if you take this guy and where is your horizon? This is the horizon.
Yes.
And you take the modes which make their way out like this.
Yeah, but then-
these will be increasingly
Okay,
as
let's-
time goes by.
fine, let's-
more
Let's
stronger.
consider this observer.
No, so that's why I said if you have a black hole horizon, let's look at it from one side. So this is Cry Plus. You have a future horizon. Look at a freely falling observer
understand.
into the future. I'm just saying the standard thing,
I
right?
understand.
Then these look more and more boosted, and that's the sense in which it is a very short distance effect. Of course, I understand it's the vacuum,
Yeah.
but it's the structure of the vacuum, as many people have emphasized, at extremely short distances, which is tied to the result coming out to be what it is in this semi-classical
Okay.
approximation. And I only say that partly to ask whether if one was to attempt a direct calculation in the bulk to see the coming back out of information, one would need to work in a consistent theory of 2D gravity down to ultra short distances, and then you could ask, is the JT model such a model? Are we sure it's such a model, etc.?
Uh-huh.
And otherwise, if you're not sure it's a precise model,
We should-
the precise statement you folks have covered?
Okay.
Alright,
Yeah.
anyway.
I'll refrain from making comments on
Yeah,
that.
yeah.
Isn't this connected to the fact that it's very hard to laticize, let's say, a field theory in a generally coherent way? Yeah. Because if one could do that, then one could get a direct contradiction. Because the entanglement of this stuff keeps growing infinitely.
Yeah.
But there was a finite sort of Hilbert space below it.
Yeah.
And
This-
yeah.
This effect is actually so related to what you said. This effect has been seen in SYK. So you can take two SYKs. No, but this okay. I'm jumping the gun now. Okay, I'm going to say paradoxical statement. So you take two SYKs that are coupled, two SYKs in the thermal state. You couple them, and then you directly compute the entropy of one SYK. There's a contribution to that entropy, a saddle, if you will, where the entropy simply grows linearly in time, and it just keeps growing.
This is a Schenker.
This is work currently being done by Stanford, Steve Schenker, and Jeff Pennington. So they can identify in the SYK model what is the contribution that corresponds to Hawking's calculation, like the wrong answer,
Very interesting.
and it just keeps growing.
And there's another saddle.
Exactly.
They see this directly in SYK.
Yes.
It's not even a unitary theory with all
Whoa.
that quenching and all that. You still see the second saddle.
Yes.
That's almost too
What
much.
is the second saddle?
So when you work in the G sigma formulation of SYK, then in this computation of the Renyi entropes, it's the same thing that I was telling you, which I'm going to talk about. So a similar set of words can be applied to the resolution, which I'm going to talk about maybe in a few days. So they compute the Renyi entropy of one of the SYKs, and there are many saddle points, many different saddle points of the G sigma action, and you need to sum over all saddle points. And
Sorry.
one saddle corresponds to an entropy that keeps increasing, and another saddle corresponds to a constant entropy. Exactly like the way I was talking about right here.
This is replica trick.
Replica trick, yes.
And this is in the eternal context.
Yes, yes, yes.
You will probably tell us about your telepresence, which is also replicatory.
Yeah,
That's
yeah, yeah.
almost too good. It's not even a unitary theory or anything.
Well,
It sees so much of the.
let me give you evidence for why you should not be too surprised.
Yeah.
I mean, in these other calculations of Schenker-Stanford about the two-point function, right? So for unitary theory, you expect all these wiggle for a single realization of SYK. You expect a thing that has all these wiggles and so on. But if you work in the disorder average theory, then you don't see the wiggles, but you see the average in some sense of the wiggles. So in some sense, even though that thing that they compute is a fine-grained thing, but it's not too fine-grained. The really fine-grained thing is all these wiggles. But somehow, even if you average a little bit, you don't just go to zero. You still find the average of the wiggles. And the statement is the same thing would apply for the entropy. The entropy would also have some wiggles, but if you work in the disorder averaged, you'll just get a smooth curve somehow.
So perhaps this is related to, maybe I should ask at the end, but just in case we don't get there. I mean, something that a vague question that I wanted to keep in mind through your talks is that in some situation like the eternal black hole or something like that, you've got a particular density matrix, you get a particular set of radiation. But if you have a black hole formed from collapse, that could happen in many different ways. And we'd like to see that the radiation that comes out captures precise nature of that state.
Yes, yes.
And you have some way of thinking of this as well.
I mean, I don't have any progress on that question, but I completely agree that to first order, one should get the Page curve of a black hole. Then I think that resolves Hawking's information paradox as he proposed it. But then there's a more fine-grained version, which is to show that there's a one-to-one map between initial states and final states. And
Since there are so many possible initial states, it sounds very hard to do
It seems like it's a
calculation to do.
I agree. But at least one should hope to be able to work around within some subspace where you consider a very small set of easily prepared initial states and show that that corresponds to that there's a one-to-one mapping between those and some class of final states. So I think maybe one can do this in the framework that I'm going to describe later, although we don't have any calculation yet.
Question. I'm sorry, I brought that up because that wheel is the details of the state, right?
Yes.
And this is just some very coarse washing
Well,
away everything interesting.
It's a coarser thing, but it's not too coarse.
It's already great that that's there.
The really coarse thing is just a coarse-grained entropy.
Yeah.
Right?
I agree. I agree.
Yeah.
It's great progress compared
Yeah.
So apart from doing the coarse-grained SYK, there are some non-perturbative effects like this ramp and so on, the semi-classical ramp. So what they're discovering now, is it in some way related to that?
It's
not completely coarse-grained, right? I mean, whatever the entropy they're calculating, from the sound of it, seems like
it is like that in the following sense. So in their plots, so the two-point function, they have something like this, and the ramp, and then the plateau. I think this was given by just a contribution from another saddle point. This was a contribution from a sum of saddle points. The computation of the entropy is more like this, in that it's just a different saddle point that contributes. And you go from one saddle point here to another saddle point there. It will be interesting to see if these other, whether a sum over saddle points is important for anything in this story.
I just wanted to come back to this issue of finiteness of the subregion. This original work of Calabrese and Cardi, they had a linear plus saturation growth, which was reproduced by Hartman and Mallasina for eternal black holes.
That was for two intervals. That's right.
Yeah. So for two intervals on the two sides,
They're connected and then they disconnect. Yes.
right, which were both finite. If they're finite, then there is one saddle which just
Mm-hmm.
And then there's another saddle which comes, and there's an exchange of dominance that happens.
Yes, yes, yes. So there's a subregion here.
Yeah.
This is one
Yeah.
RT surface versus the one that just ends there, something like this, right?
Yeah, that's fine.
Yeah.
Along the boundary, I mean.
The entropy of this is this boost invariance, and so the entropy of this is constant, but the entropy of this grows because of the growth of the interior of the black hole.
That's right.
And so that's why it does this and that, and this is essentially what's going to happen in our case as well. It's essentially the same phenomenon.
But you probably have infinite subregions on both sides. The reason why you have eternally linearly growing thing is because you have infinite. If you had finite subregions on both sides, then it would be linear up to some point, and then it will saturate.
Oh no. The point here is that this thing that keeps growing infinitely, that's a wrong answer, right? The idea, the statement is that this calculation is wrong somehow. There's something that needs to come in and correct it that gives you this other contribution. So that ultimately we want to reproduce this, but in our context, so far I have not told you guys what is the effect that tells you that the entropy has to go down and follow this curve.
But I'm saying a normal conformal field theory calculation can have an
Oh.
eternally linearly growing thing.
Yes. Yes.
Which, however, can be cut off and saturated eventually if you take into account the box effects.
Sure. Yes. Good point. But in my case, it's not in a box. It lives on a half space. So in principle, let's ignore what it's entangled with. In principle, the entropy of the CFT can go arbitrarily large. Right. So that we agree with that.
Yes.
The reason why it's a paradox here is because the thing that it's entangled with has a finite density of states. That's the paradox. The paradox is not that the entropy of the CFT by itself is going large. It's going large in this context that is entangled with this thing. Okay, these guys are pointing at me.
No.
No, we were wondering if you, we can talk a little bit, would you like to have your beautiful lectures written up as part of a series? We had this tradition, for example, David Tong had come in and given, actually, he was on sabbatical, so over a few months, in that case, on the quantum Hall effect,
Okay.
the Tata lecture. So if you like, we can have your lectures as part of the Tata Infosys lectures written up. We can get some students here to help you.
Okay, as long as I'm not writing it, please.
No.
So the protocol would be they'll take notes and then they'll make some tech notes and then send them to you.
Okay, yeah, that'll be very nice.
Muni and Sunil can do that because they're working on all of this. Yeah. What do you think? I'm volunteering you guys. But it's a good chance for you to really, you're already here today and it's recorded, so that's a great help.
Yeah.
Okay, great.
Yeah, maybe Arvind can do it.
Oh, sure. No, I don't know if this was asked while I stepped out, but just to ask you, Ahmed,
Yeah.
we can go for tea if you like yours. In his strings talk, Steve Schenker, for example, suggested strongly that perhaps the JT model actually captured the average over all the ground states and so on. That kind of behavior. And it is true that you get an ADS2 typically in situations with some large ground state entropy. That hasn't played any role so far in what you've said.
So the ground state entropy is inside this. Including it or not including it just pushes this further up, and so the transition just happens at a later time.
But could it be that the JT model per se has a limitation in terms of
Yes.
describing unitary
Yes.
physics?
I think it's a statement. Sorry to cut you off. I think it's a statement about the wiggles. So this is going to give us a very nice, smooth entropy or evolution of the entropy. But if you were to do this for a single realization of SYK, then you expect something much more wiggly. Yeah.
But broadly, you say it will give this
Yeah.
smoothing out.
Yeah.
that you-
Actually, I did this calculation with Yeah, this field is actually very fast. Everyone's scooping everyone else. We already did a while ago, Brian Swingle and I, and Alexei Melikin, a graduate student, we actually did the calculation numerically for the entropy. Just a very quick calculation for,
in this model.
in SYK at some large n, 40 something or something like that. And it looks like this. So then we take a thermal density matrix, and then we coupled it to something, and we let it just evaporate, well, in thermal equilibrium. Actually, in our case, I forget the precise details of the coupling and the energetics and so on, but you get something like this. You get an entropy, which is, does something. There are wiggles, but it really follows this behavior.
I see. So you took two SYKs to begin with, coupled them in some thermal entangled state, and then you allow one to radiate out the analog.
Yeah.
And from field theory, it couldn't have been. It's just a field theory calculation.
Well, what we just did was, that's what you meant by field theory, just an SYK calculation.
Yeah.
Yeah,
So
quantum.
it couldn't have been anything else, right? I mean, it would have been a violation of.
Yeah, exactly.
Exactly, extremal calculation has a large degeneracy. The choice of this dilaton field, namely the phi r in these coordinates, that sort of breaks that choice, and then you don't have the degeneracy.
No.
Sorry.
Phi is the dilaton, right?
Right.
The radius of the sphere.
Right.
You always have the ground state degeneracy anyway.
Yes, so if you are exactly at extremality, there was a great amount of ground state degeneracy,
Right.
and now this is slightly away from extremality.
So you have the ground state plus a little bit more.
Yes, ground state plus a little bit more. Now, the question was, the thing that I was trying to say is that you have said earlier at some point that could there be that the actual description is the averaging is sort of coming from the fact that you had some sort of a very large degeneracy in some sense.
No.
I mean, I thought what you were saying was that perhaps the smoothing out of the wiggles
Right.
is due to that kind of averaging.
You said at some point,
Yeah, that's what, I mean, I was wondering what is the effect of that.
Yeah, the statement is, okay, I'm not sure I followed what you were saying, but the statement is JT gravity is what you get when you start with SYK and you do a disorder averaging.
Over the coupling of the
Average over the coupling.
This is one story.
Yes.
That is their
Okay.
story. Now,
Yeah.
could it be so? The question is, could it be that it is already natural when you are working with JT gravity? Is it a natural prescription that you don't even expect to produce the whole of the unitary behavior of
Yes.
the SYK model?
Yes.
It's natural. So the question is it natural in some sense? The way it is phrased that if JT gravity is everything, then it's not natural. Then you will say that you have to average over couplings of SYK to produce it, and then you are having a trouble. But is it already a natural description when you are describing in terms of JT gravity? This is the second part.
Wait, you get JT gravity after being SYK averaged over.
Right. So this is let's say the one part of the
Yeah.
story.
Yeah, maybe let me say one more thing, and then which is because that's something some of us have been thinking about, which is JT gravity appears in contexts where you don't have a disorder average, as in string theory near extremal black holes, right? And could there be some analog of disorder averaging there? And there, the thing we're trying to work about a little bit is you have a large ground state degeneracy, and it
Okay.
could be that it's only after averaging over the ground states that you get a description which is the JT model. Question remains to be seen. But in that case, if it's true in some sense, then it could be that the individual ground states might give you the analog of a very wavy behavior, but the model as a whole gives you the smoothing out. I'm just saying in case this was part of what you were.
This is exactly the kind of.
But I'm not sure, I mean, we're not starting with a ground state. I mean, we're starting with a thermal density matrix.
But very close to extremality.
Yeah.
So you do have a huge, at least when you start, you have some entropy which goes linear indeed, but to that is a big S0 part.
Yes.
Right? And The question is, does the JT model describe the average
Okay,
over
okay.
all
Yeah,
the
yeah.
ground states or not?
I see, I see, I see.
You know, yeah. So if you look
I
at
see.
some of these models, for example, of Ashok Sen, where you get ADS2s with intersecting branes, where you have quantum mechanics living at each of the intersections, then you have many possible such intersection points, etc., and that accounts for the entropy. And the question is, does the quantum mechanics around each of them, is it well described by JT or the average? And then how does, so
I see.
that could be part of the context of it.
Mm.
Yeah, these are isolated vacua.
And these are isolated vacuum.
So the average would then have to go over the bumps.
You have to go over the bumps, but it could be that you don't have to go over the bumps. That is, the individual, the parameters of the quantum mechanics around each of the isolated vacua are different. But there's a sort of average behavior, even though tunneling is not important. I mean, it's the kind of thing which needs to be worked out. But it's worth looking at. We'll have to see how far you get to it. But in the ADS3 context, anyway, we can stop. There's something interesting. In the ADS3 context, it might be something worth doing, because if you look at the extreme VTZ, which also has the ADS2, in some large central charge CFT, then you have the ground states which are just carrying, say, left moving momentum, and you have some big degeneracy. And the question is, from the CFT, can you understand how the dynamics of the Schwarzschild mode, which obviously is tied to the Vera-zero algebra on one side, how does it arise precisely, right? Is there an averaging over all the ground states involved there or not? This is a pretty sharp question, actually. In fact, if I posed it to all of you in this room who are real experts, you should probably do it from
And I think
breakfast.
if it is true, then there is then the first fact that JT gravity as it stands, it produces only an average SYK, that would be no mystery. I mean, that would be the.
Yeah, so
Then
this
I'm
one,
totally
how
satisfied.
why haven't you done it yet?
No. I know. I'm just saying.
So Vijay Balasubramanian has looked at the D1, D5 system
Yeah.
and asked not about the spectral form factor, but about the two-point function. Because D1, D5 has a large ground state, okay, the two-charge system as well as the three-charge system. So but the conclusion is not clear. But it's this is a very good system. So actually we have.
Okay.
We are looking at that thing. We also discussed with Shiraz about that one. And
So this was older work of Vijay's or more recently?
no, it's recently. I mean,
Oh, I
it's he
see.
called it
In the same
It was
with-
yeah, it was of chaos, 2017 or something. This was done right after this spectral form factor papers.
I see. Okay, well, interesting. Okay. Sounds great. Very nice. Thank you again.
Yes.